Okay, so seek to seek, seek to seek. So what is seek to seek model? So let's look at it. Um, we have previously seen that RNN, which is recurrent neural network, they can be used, to process sequence of information, but uh, the information they can process is basically in one direction. Yeah. Um, And what they do is, as we call them, language models. And the task of language modeling is just predicting next word. That's what we talk about. If you remember, uh, language model basically what it does predicting the next word from left to right. That's what language model does. But if you remember language, um, it actually depends on what you say previously and the next. For example, if we want to analyze something that I said right now, we need to take context on what happened in the past, right? That means for us to understand language, to do language modeling, uh, to do something like language that we understand, we need to have model that understand something that has been said previously and something that has been in the future. That's why the classical or normal RNN was not able to process, stuff. And then we have what we call bidirectional RNN. So bidirectional RNN is basically, uh, you know, extend the classical RNN in two direction. That is, it has the left and backward. You can see this one is front and back. You can see back and front. That's bidirectional RNN. If you remember, we have seen some of the problem with classical RNN. One of them is that. It's slow, and one of the here we can see that it only goes in this direction forward, right? The classical RNN. So to solve that issue, one of the issue with RNN, we now have bidirectional RNN, and in this way, it actually had access to tokens from both left and right. But again, can this all solve the issue we have for RNN? No. Let's look at it. It cannot, and as we see, just give me. You can see this is RNN. So the RNN we have, we can see here we have in RNN we have also LSTM, which we have different kind of RNN version by LSTM and by GRU. They are all, they are here to solve the problem of, RNN, classical RNN. One of the issue also we talk about is, RNN, if you remember, is that RNN cannot capture long-term dependencies. What I said is if you have a long sentence, therefore, what is at the end of the sentence, if we use a classical RNN, it may forget what is at the beginning of the sentence. And we know that language must have this diff dependence. What you say at the beginning of sentence must have, relation with something at the end. So in that way, we have what we call, multi-layer RNN, which is also stack RNN. If you look at them here, we have stack RNN. So we have one RNN here, we have another RNN layer, we have another layer for RNN. And these allow, language model to capture more complex structure. If you remember in computer vision, the more number of layers we have, the more capability of the network is. So this, solve the issue for where we have a single RNN that is cannot be able to capture long range dependency. So what we are talking about, remember, is we are talking about still the RNN, which basically some of the issue that solve the issue for RNN. So we can see here we have stack RNN, which basically is LSTM, which is variant of RNN. We can see there's a stack. So we can see now we have some ways to solve the issue of RNN. Number one, we have seen that uh, RNN, because it's one direction. So to solve those issues with classical RNN, we can use bidirectional RNN, which we can have by LSM or GRU. That is one. Number two, to solve the issue of RNN does not capture long-term dependencies, we can use stack RNN, where we have multiple RNN stacked together. That is solve the issue of that. Now, the LSTMs, which is called long short-term, memories, are basically one of the solution that was, future to solve the issue of, RNN. In 2023 to 2025, LSTM started achieving state-of-the-art results. So when we say LSTM is variant of RNN that introduced some other stuff, but in this year, the RN LSTM started to become the, you know, best architecture that solve real-world problems. In some of the real-world problems RNN solve include handwritten speech recognition, machine translation. But it even became the most dominant approach in NLP in this year, 2013 to 2015. So if you are doing NLP and you hear people saying, I've used LSTMs, that's in those days. LSTM was good in those days. But now from 2018, 2015, the current architecture that became dominant for all tasks is transformers. Yeah. So we have seen now, okay, RNN is not good architecture. It has a lot of problems. So LSTM comes to solve those problems from RNN. Yes. Now we have seen that. But now today, LSTM had become the story. For example, if you look at it, in WMT, which is basically WMT is machine translation tags or conference or shared tags. In 2014, there are zero neural machine translation system. In 2014, when we say neural machine translation system, it means in 2014 there was even no LSTM or RNN, because LSTM and RNN, they are neural machine translation system. So maybe there are statistical machine translation system. But in 2016, the summary report contained RNN 44 times. That is, in 2014, 2016, there were RNN in the architectures, in the people's paper, up to 44 times. So in those days, you can see RNN was very good. People were using it. But in WMT 2019, because WMT is a yearly competition to solve machine translation problem. So in 2019, RNN was mentioned 7 times and transformer were mentioned 105 times. That is in 2019. That means today, in 2015, if you find the report, you may see no single paper that works with RNN. All the papers work on transformers. This is just to tell you that now we are moving ahead from classical approach to solving NLP problems, LSTM, RNN, all those olden approach, nobody used them. What we are using now is what is called transformer, and that's where we are heading for. So this is just telling you the story about, some of the things we have. So you can see, if you remember in RNN, we talk about vanishing gradient. So LSTM solved that problem, right? They also improve long-term redundancy, but just still, they are not that good enough. They cannot solve a problem of what we call, seq-to-seq. One of the difficulty for, LSM is handling variable length output. Handling variable length output sequence. Output. Does anybody know what that means? Anybody know what this means? We say LSTM has one difficulty, handling variable length output. So what we mean by this is that, remember, when I say variable length output, is that maybe for machine translation, if I give like a sentence, I love this card, and then I have another something sentence, I love this card, this is beautiful, just okay. Okay, can you hear me? Can you hear me? Hello?
Yes, sir, you're
Yes,
audible.
we
Yes,
can hear
sir.
Okay.
you.
Can we hear
Okay.
you?
Okay. So what we said, difficulty handling variable length output is that if we look at machine translation, different sentences, different have length, right? So for example, I can have one sentence with 20 words, one sentence with 30 word, one sentence with 50 word, right? And when I translate these, they must have different output, right? So in LSTM, everything that goes into the LSTM must have the same length. So that's one of the issues. But we want to have a solution where we have problem where we all we need to do is we give sequence and we have another sequence output, immaterial of the length of the sequence. That is called seq to seq. That is, I give a sequence, maybe length some sentences, and give me equivalent sentences. Just give me another sequence. I don't care about the length. That is what we call seq to seq problems. So LSCM cannot solve Seq2seq problem. So Seq2seq problem include translation, summarization. For example, in summarization, you give a language model text and you ask it to summarize, right? So you can see this text you can give it may have variable length output. So you just give it like a single text and it summarize it. In translation, you give it a sentence. In Hausa, you ask it to start translate in machine into German. It give you this, right? Speech to text. So these LSTM fall short. It cannot solve this kind of issue, and that's why we need a better approach to solve this problem. So LSTM improves security model by removing long-term dependency, allow model to process sequence token by token, maintain memory, capture long. So it's still LSTM has this advantage. It has long-term dependency because it's long. That's why it solved the problem of RNN, and also it has some memory where it can remember something in the past, but still it's for short. So we need a better approach. So but LSTM can still be used in some stuff like sentiment classification, um, speech recognition. For example, in sentiment classification, why is it we can use LSTM? Because in LSTM you give a sentence. In sentiment classification you give a sentence. We need to give the class. For example, is it positive, neutral, or negative? Because this is not sequence. If I can give you text, I say what is the class for this, you say positive or negative, right? So this is not sequence. You can see these tags typically produce a single output, right? Yeah, a single output, right? For example, speech recognition. For example, I can give this speech, I can say to recognize which kind of this. It just give you a single output, not giving you a sequence. So LSTM is good in typically in where the output is single output, right? It's not a sequence of instructions. So LSTM is being used quite good in this application. So, but this is a duplicate slide. Many real-world NLP require sequence-to-sequence mapping, not a single output. So, example of these tags are translation and this, and therefore, these are some of the some of the issue or real-world problem where we need variable length input sequence to variable length output sequence. For example, in English sentence, to give me French sentence. So you can see this is translation. You may have different output on question answer, and these are all the different ways. Now, the thing is, if you look at this, which I've been saying, input sequence, if we use LSTM, it just gives us a single output. But what we need is input sequence. We need another model here to give it an output sequence, right? So we need input sequence, we need a model to give it output sequence. Therefore, LSTM cannot do that. So what kind of model can we do that can give us output sequence? And an idea, what kind of model? Before we jump into the transformers, we must have something that people create to, yeah. Anybody can give us an idea? Okay. So one of the idea that people use before is to use two LSTM instead of one. Um, this is solution that was proposed that we call encoder decoder architecture. Encoder decoder architecture. What is basically used is two ideas. Number one is to use encoder for the LCM and use encoder for LSTM. So if you use encoder to encode, entire sequence, which is sequence, and then you use decoder to generate the output sequence. That's the idea. So we have what we call encoder-decoder architecture. What this does is that if you look at this, what I said is the first thing is the encoder, which is could read the entire sequence. When it reads the entire sequence, it compresses the entire sequence into what we call contextual vector. Okay, let's look at it. So you can see this is one architecture, which is encoder, and this is another architecture called decoder. So the LSTM architecture, the text can come inside here, and LSTM comes here, right? And now what happened is that we have another thing called, we have another thing called uh, vector, which basically is now passed to the next one. So whatever is here, the final thing here is passed into decoder. And this final thing that is passed to decoder is called state vector. That is all the information here in the LSTM encoder is now compressed into a single vector called state vector. And the decoder here will now decode everything to give output here. That's what we mean. The encoder LSM reads the entire input sequence, compress it into a context vector. So, and now the LSM decoder is. And this context vector, the state vector, is sometimes called hidden state. The final state this vector represents meaning of the whole sequence. So this final state vector represents the meaning of the whole sequence. So for example, if I have a sentence here, pass it here from one word, another up to the last word, and now everything now passed into this. So the whole meaning of the sentence here is now compressed into this. And you can see the hidden state become the initial state of the decoder. This vector is often called context vector or state vector. So this is the idea where we have what we call encoder decoder. It uses an LSTM to understand the input and then another LSTM to understand the output. So you can see this is basically what it does, because you understand, we need to have an architecture that generates sequence and also another output architecture that generates output sequence. So they come with an idea. Okay, let's use LSTM as an encoder and another LSTM as decoder. So that's what we have in this one. So you can see that encoder decoder solve the problem of Seq2seq modeling for variable length input and output. So if in that case, encoder decoder solve this issue that we say we need actually a better architecture that can solve the issue of Seq2seq. So encoder decoder solve this issue. Don't forget here that we are taking this, historical perspective, because nobody now uses encoder Seq2seq model, but we are laying the foundation that will give us the understanding of what will come in the next part, which is language model. So this is classical NLP. In those days, this is how people do NLP. So we can see here, this Seq2seq form the basis for advanced sequence-to-sequence model like attention model, GPT, transformer, and BART. So this architecture that we have, something that will do for encoding, and then we have something that can be do for decoding, give us the basis of what other architectures have been built, such as transformer and GPT models and BART architecture. Because all these architecture, for example, are like GPT models, like chat GPT and all these, they are, maybe we can say, encoder decoder architectures. We will see all this about them. So yes, so this actually is a good way to do that. And these Seq2seq transformer based without the RNN, we can see later model introduced improvement by LSTM. The encoder capture both left and right context. So you can see here we're talking about we need architecture that can capture by both left and right. So if we use by LSTM inside our architecture here, For example, if we use by LSTM here, this is normal LSTM. So if we use by LSTM, so it can capture both the left and right. So here is the classical representation of a encoder. But if you have by LSTM inside, not vanilla LSTM, so it can capture both left and right, which is needed for that. Attention mechanism to improve long range dependency issue. So even though we are having modern Seq2seq here, Seq2seq here, for example, we have decoder, we have encoder, and have decoder. Now, inside here, this architecture, if you have LSTM or by LSTM, they still have the issue of long-term dependency, meaning that they cannot capture long-range dependency in the language. So the new thing that was introduced to solve the issue of long-term dependency is what we call attention mechanism. It basically overcome long-range dependency issue. So if you have a sentence, and even if the sentence is very long, even though it's very long and LSTM architecture cannot solve that issue, now attention mechanism is now implemented that solve that issue. And attention mechanism was in 2025, in 2015. And then, another thing that comes is transformer-based Seq2seq. So transformer architecture come, but in transformer architecture, there is no RNN. It's Seq2seq modeling. For example, we can say that this is Seq2seq because we input sequence and we have output sequence. But inside our architecture here, you can see here we can have LSTM, we can have RNN as part of the architectures here. But what we're gonna have here in the another Seq2seq based Seq that is transformer based Seq2seq is Seq2seq model but without any RNN architecture inside it. So you can see these are some of the things that have become as a way to introduce more improvement in Seq2seq model. So these are basically what we have been talking about previously. For example, we talk about RNN problems that RNN cannot solve long range dependencies. RNN, cannot. Yes, go on, Abdul Bala.
Yeah, can you hear me, Doctor?
Yes, yes, yes.
Oh, I just wanted to know if it's possible for someone to have like an hybrid architecture, combined LSTM style recurrencies with maybe attentions that says to performs more outperforms the transformers that we're currently having in the NLP benchmark. Is that possible?
Can you come again the question?
Yeah, can you hear me now?
Yes, yes.
Yeah, what I'm saying is, can we be able to have like an hybrid architecture that combines the LSTM style recurrencies?
Hybrid architecture that combine LSTM and what?
With the attention.
You are breaking, engineer.
Sir,
Yes, yes, Lukman.
his question was mostly whether you can combine attention with the Seq2seq model and see whether you can get better performance
Yes,
as
yes.
compared to
Okay.
transformers.
Yes, yes, yes. So what? Yeah, that's a good question. Actually, that's a good question. Uh, yeah, that's maybe the good question. So, let me recap what we have. So look at the problem. We understand the problem of transformer, right? RNN. Can somebody tell us the problem of RNN? Maybe in the chat. What is one of the problem for RNN? Can you tell us maybe in the chat, or you can unmute yourself and tell us?
It cannot capture long-term dependencies.
Okay, good. Okay, okay. Now you talk about one. Now, what architecture now solve the problem of cannot capture long-term dependency?
The LSTM.
Okay, good one. LSTM. Um, what about GRU? It also solved the issue for RNN, gated recurrent unit, GRU. So LSTM and GRU, they are all architectures that solve the problem of RNN. Their architecture is basically based on RNN. They all try to solve that problem. But now we said, okay, we now have LLCM and GRU that solve the issue, like, for recurrent, for the issue for, long-term dependencies, long range, but they cannot solve the issue of, okay, now what motivates us to now have Seq2seq model? Can somebody answer us? What motivates us now to have Seq2seq model instead of LSCM or GRE? Who can tell us? What motivates us to have from RNN? We say, okay, RNN is not good. It's not solve. It cannot solve short dependency. We now have other variant like LSM and GRU. But now we say, okay, LSM is still not sufficient. We need to do something, and we come up with Seq2seq. Can somebody tell us why do we come up with Seq2seq?
The LSTMs and GRUs, they only produce single output, and they cannot give like when the output is having variable length, they are not good at that. So that's why we come up with the sequence to sequence, in which we have an LSTM for the input, another LSTM for the output.
Excellent, excellent. Ashi ana ganewa. Yeah. So now we have Seq2seq. But in Seq2seq now, we talk about something, because in Seq2seq, it's not that the architecture is changed in Seq2seq. Look at it. Let's go back. In Seq2seq, the architecture is not changed. In Seq2seq, if you remember, it is still LSTM inside. We have encoder, we have decoder. Is that correct? So the architecture is not changed. It's just we have encoder that give text sequence, and decoder give us sequence. But in LSTM, we still say that LSTM has some problem. What is the problem for LSTM? Still. Okay, let me say something. Let me say something that I didn't explain. So if you look at this one, we have LSM encoder and we have LSM decoder. So what is happening here is that you can see X1, X2, XT, meaning like it's a sentence, sequence of sentence. Like this is the first word, the second word, the third word, like, something like, up to da 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 dash. Can you see da da dash? Now, one key thing here is that if we have long sentence here, a very long sentence from X1 maybe to X20 or X50, all the information in one sentence is now composed into what? Can somebody tell us what is composed into what?
Like single vector.
So now, when we have single vector, everything composed into single vector, do you think there is disadvantage in that? Like, if you have very long information, and that long information is now represented in a single vector, and this decoder can use that single vector to decode whatsoever inside, do you think is there any problem with that?
Yes, sir. Maybe some of the important information might be missed during the course
Exactly.
of the compression.
Exactly. So I would just want you to look into maybe ChatGPT or something. Just look at what is the problem of state vector in LST and encoder decoder LSTM architecture. Tell me the answer. It's okay for you to use ChatGPT. It's okay to use any LLM. What is the problem of hidden vector or state vector in encoder decoder or context vector? Username context vector. What is the problem of? Let me check. What is the issue using context vector in encoder, decoder, Seq2seq, OLSTM architecture. Yeah. I have a question here. Type, so ask your chat GPT also, ask it what is the problem, and tell us the answers. Yes, anybody can tell us the answer?
Eh, Can I read it, sir?
Yes, yes.
Okay, so just from what I found, it says that using single pix size context vector or hidden state to summarize long input sequences in LSTM encoder decoder architectures creates an information bottleneck. So this causes performance to degrade on long sentences as the model forgets early information. That is banishing gradients in brackets and struggles to compress complex context into a static representation.
Good. Can we read something that also Bala Marigab wrote in the chat? So basically, it creates what we call information bottleneck. Yeah, leading to loss of information and poor performance on long sequence. That means if we have a very long sequence of information, this context vector can lead to loss of information because this decoder will, try to solve. So that means the encoder decoder architecture that solve the issue where we can have Seq2seq model is okay, right? To have Seq2seq model, encoder decoder solve that problem. But one of the problem now comes is that the state vector that compress all the information, that take all the information from the previous, create what we call information bottleneck if the sequence is long, and therefore we're gonna lose some information. As we can see in the chart, the context vector create an information bottleneck by compressing the entire input sequence into a fixed length representation, leading to information loss and poor performance on long sequence. So now that's, we have now another problem that we want to solve. How can we solve the issue where we don't have a single vector? um, you know, that is the problem we want to solve. And that problem is now being solved by what we call attention mechanism. Yes, that problem is now being solved by what we call attention mechanism. So what attention mechanism does, to instead for us to compress all the information into single vector, the attention mechanism, if you want to translate this word, for example, if this word is called aboki, and you want to translate it to English, maybe friend, now the corresponding decoder here will now try to get attention in this output. It will have some input, it will have some output here that relate directly connect to here. And also this one will have some output that, it will have some attention to some stuff we will see in the next. Rather than decoding all this output into a single vector, we're gonna have some attention mechanism where the if you want to translate a word, it will map attention to a particular word to make sure that the word that is more important at that point, to make sure that it translate that very correct, translate it correctly. So that's the next natural step, that is we have seen Seq2seq. As I told you, this is something like, we are seeing as a progressing, that this is something basically that, we start looking at classical NLP, and now that lead us to transform. Instead for us just to jump into transformer, so it's good to give us this story, why this. So that's why now we're going to look at what we call attention mechanism. And now if we look at attention mechanism, we now still look at some problem whereby another architecture, another stuff called self-attention and multi-head will solve that issue, and which all this issue as self-attention will now be integrated and finally into the architecture called transformers. So yes, to answer your question, Bala engineer, yes, we're gonna have attention mechanism now plug into the architecture. We'll have so basically, let's look at this. Oh, okay, okay, this is something that I want to talk to you. One of the most widely used machine, architecture that used to solve Seq2seq, which is machine translation. Let's rush to it because we have 10 more minutes. Let's rush into this, about machine translation, and then tomorrow we'll start attention mechanism. So machine translation is the task we know of taking one sentence and translate it to another, right? And the research for machine translation has started long ago, since 1950, before even AI was used, that. And, it was basically used at that point, to do using rule-based system, doing word substitution. For example, if I want to translate uh, Hausa to English, I will look into what is the translation for the word, particular word, and replace it with that. That's what it done. So we have three different ways to do machine translation in those days. We have rule-based, we have statistical machine translation, and we have phrase-based SMT. These are basically the approaches that you use to do machine translation in 1950s: rule-based, statistical, phrase-based. But the problem is that all these, they are not good enough. They are rigid rules, meaning that the rules, because you use rule, you take one sentence, a word from this to translate it, and they cannot generalize well. For example, if I translate a particular document, it cannot help me to translate another document, which good generalization. So from machine, from that we have, in 1950s, that is what we use. In 2014, we now change into, using machine translation, using neural machine translation. That is using what we call Seq2seq, for example. You can see this paper, Seq2seq, is the one that comes up with the architecture we are talking about, Seq2seq. So Seq2seq learning with neural network. This is a paper from Google, I guess. Yeah, that demonstrated that a single neural network will be trained end to end for translation. So this is a paper. You remember we are talking about Seq2seq. So this paper introduced the architecture for Seq2seq. It is the one that introduced the architecture we saw about Seq2seq. And also another paper, neural machine translation by jointly learning to align and translate, introduce the architecture of introduce attention mechanism. So aligning, putting together Seq2seq architecture, engineer, I think you asked this question, putting together Seq2seq architecture with attention mechanism, that is what actually works, that's what makes things really different in those years. So yeah, so that's neural machine translation. So let's look at that neural machine translation. Neural machine translation is that, let's assume here we have encoder, here we have decoder, right? So you have your encoder, you have decoder. And we can see here, encoding the sequence and provide hidden initial state. This is what we have, for example, what I talk about hidden state, which actually was a problem and it cannot be used that, um, you know, um, giving the network some view of sender and produce some. Okay, yeah. So this is basically what I talk about, where we have, encoder, decoder, and that can be used to solve that one. And if the input is sequence, as we call it Seq2seq, this is what we already said about that. We already know that neural machine translation, how can we train it? Like, how can you train machine translation system? Right. How can you train machine translation system? We know if you want to do sentiment analysis, you need to create data, training data, and test data, right? But in machine translation, what you need to do is you need to get a very big parallel corpus, um, get a big parallel corpus, and then using that parallel corpus, you can do machine translation, and also you can do a lot of other stuff such as data argumentation. Does anybody knows what is parallel corpus? Parallel corpus. If we talk about machine translation, we have something called parallel corpus. Do you all know parallel corpus? Anybody can tell us what is parallel corpus? Oh, you don't know what is parallel corpus?
It's just like a direct translation.
Eh?
It's like a direct translation. You have them in different languages. Then you
Okay, so parallel corpus, we said, like in machine translation, the way we have our data set for training is we use what we call parallel corpus. So a parallel corpus is if I have, for example, this is text in English. So this will be text in Hausa if I want to train machine translation for Hausa system. So you have I love you here, for example, in English, you have I love you here in Hausa. I love this car, you have in English, you have I love this car in Hausa. I hate this car in English, I hate this car in Hausa. So this is what we call parallel corpus. So in training machine learning system to do machine translation, we prepare a parallel corpus to train that system. That is what we call parallel corpus. Um, Unlike other tags for NLP, where you don't need parallel corpus, maybe you need only maybe a data set with class. For example, if you want to train sentiment analysis, you only need data input with class level. So let's go again. We also have something decoding for decoding. If we talk about we have encoder, we have decoder. So decoding anything here from input here, we have many decoding strategies. You have greedy decoding, beam search decoding, sample based decoding, which we not discuss a lot here. So yeah, the very big success story for NLP, as I said, in 2014, the very first paper for Seq2seq published in 2014, and Google in 2016 switched from previous because they were using statistical machine translation, but because this paper bring a very good way to do machine translation using Seq2seq, they now Google switched to neural machine translation from 2016 in 2016, and then everyone is using Seq2seq architecture to do machine translation. So you can see even Facebook, Microsoft, Google, they were using Seq2seq. Yeah, this was amazing. SMT system built by hundreds of engineers over the year were outperformed. That is statistical machine translation. So we can see like this is a big stuff. Recent, just 2016, people now adapt no change to neural machine translation because of this success from Seq2seq paper. Now, but one thing we should know is that if you want to do machine translation, African languages, they do not have parallel corpus to do machine translation. So there are many ways, okay, this is an example of parallel corpus. For example, this is how are you in English, in French, how are you? I'm learning machine learning. So this is parallel, what we mean by parallel corpus. So for you to train machine learning system or system to be able to do translation from one language to another, the very first thing you need to do is to get parallel corpus, and this is how parallel corpus is. And for example, for Hausa, we do not have enough data set for parallel corpus. For example, you can get a book where you have English language and corresponding, Hausa. That means if you want to do any NLP task or machine translation system, the first thing you need to do is to get a parallel corpus data set, which are in very tedious and something like that. So this is one thing you should know. Yeah, so this is basically something about what is parallel corpora, and it can be unidirectional. One language is translation into another language. It can be bidirectional. Translation exists in both ways, or multidirectional. That is one language translated into, multiple language. So for example, we can have English, and then that English can be translated into German, Spanish, French. For example, here EU regulations, because EU regulation we have in EU, we have French, we have Portuguese, we have Spanish. So something written in English is intended to, so we have multi-directional. So the backbone for any machine translation system is parallel corpus. And so you also need to know the requirement for good parallel corpus. It contains authentic language data. For example, if you want to create, parallel corpus for Hausa, you need to get a very authentic data, not, artificially generated. For example, not data that created from ChatGPT, also because it will not be authentic. Also, it must be representative of different discourse. So, for example, if you want to create machine translation data, don't just go and create data from sport, or just don't go and create data from health, from different one domain. So the data should be formal, informal, technical, conversational. Technical, maybe you can involve data set, parallel corpus about health domain, about football domain, about many different domains, so that your model can be able to generalize from different tags. So that's it. Because when you have poor quality data, your model will be also performance of your model will be poor. So this is an example of early parallel corpus for statistical machine translation. So you can see this is like in 2014, I think, also. No, 2004 also. So this is, parallel corpus example. So one key thing you can get, if you want to work on machine translation, for example, for Hausa, you can have, create a parallel corpus for Hausa, for example. This is an example of machine translation, for example, for African language. So, yeah, this is an example of our paper. A few thousand translation go a long way, leveraging pre-trained model for African news translation. We also have another way to get more data. For example, if you don't have enough data for your language parallel corpus, there are a lot of ways to get more data. One of our approach is called data augmentation, where you can expand your data set by creating more examples. So what we mean by data augmentation is that, let's assume I have, um, you know, uh, I have maybe 100 examples, 100 sentences, parallel corpus, 100 sentences from English to Hausa translated, right? And you want to expand this data set. We use another approach called data augmentation. Who can tell us what is data augmentation? Anyone knows what is data augmentation? Okay, use your chat GPT and tell me the answer. Data augmentation.
So data augmentation is more like increasing the size of the training data set by either modifying the existing one or maybe tweaking it.
Okay, is that Lukman? Who gave this answer?
So how
Oh, Bahari. Okay, yeah. Um, Yeah, data augmentation is basically a way to expand the existing data set. So that we have different kind of data augmentation approach. For example, if you have data set that is parallel data, as I said, if you have like 100 example, 100 parallel sentence, and you can want to expand that data set to maybe 200, 300. So that's goal for that: increase data size, more example, improve model relevance, introduce linguistic variety, address class imbalance. For example, if you want to do you know if you want to train models, and in your model for sentiment analysis you have positive, negative, and neutral. And the positive you have, for example, 1000, and neutral you have 100, negative you have 100. So you can see that's class imbalance, right? So you can use data augmentation to oversample minority classes to those 100 negative, neutral come to be like 800 or 900. You can use data augmentation approach. So there are different kind of approaches for data augmentation. One a very good project is one can do maybe a paper, data augmentation for low resource languages. Data augmentation for low resource languages. For low resource languages. Yeah. So data augmentation for low resource languages. So maybe, for example, you want to work on African languages because they are very low, low resource. So one can do, a review paper to review approaches for data augmentation for low resource African languages, and would be a very good, paper that one can, if you are interested to do. Yeah. So data augmentation, as I said, there are many approaches for data augmentation. One of the approaches for data augmentation is, back translation. So what is back translation? So a back translation approach is that, for example, let me show you example of this a back approach. So for example, now if I have this, if I have this, just give me a second. Um, um, all right. So for example, if I have this, oh no, excuse me. Um, uh, why can't I write? Um, okay. So for example, I have a sentence here like this. Oh, no, no, just excuse me. Okay. So let's assume I have one sentence here, and this sentence is in English, right? Um, right. This sentence is in English, and or maybe this sentence is in Hausa, right? This sentence in Hausa, and back translation means translate the target language in sentence back to source. So I can take this sentence and now translate it into English. So this is Hausa, and this is what? English. How many sentences do I have here? How many sentences do I have? I have parallel sentence one, right? I have parallel sentence one. This is Hausa, this is English. So back translation is that I can take this English that I have translated and now translate it back to Hausa. Can you see that? Now this English is now translated back to Hausa. So you can see now I have another sentence in Hausa. But this Hausa, original Hausa, I translate to English. Now this English correspondent, I now translate it back to Hausa. There will be chances that all this Hausa and the Hausa one, they are the same thing, but they are not written exactly. Is that possible? Is that possible? This one and this one, they mean the same thing, but they are writing, they are not exactly written. Is that possible?
Yes, sir.
Yeah, it's possible.
Is that
Yes.
possible?
Yeah, it's possible.
So
It's
now
possible.
you see from one sentence, you have two sentences. So you now do data augmentation. So if you have 100 sentences, if you do data augmentation like that, you have 200 sentences for Hausa again. You expand your data. That is data augmentation. Another one is paraphrasing. So paraphrasing is basically I give a sentence in Hausa. For example, I say in Hausa, zan je kasuwa gobe. Zan je kasuwa gobe. Can you see that? Zan je kasuwa gobe. So you paraphrase it, you write it in another word. To watakila gobe na je kasuwa. Can you see? Zan je kasuwa gobe. Zan je kasuwa gobe. So sai mu iya rubuta shi you can paraphrase. Gobe watakila in je kasuwa. Can you see they mean the something? So you now paraphrase. You can take, if I have this one sentence in Hausa, I can now paraphrase it. When I paraphrase it, I have one sentence in Hausa. I paraphrase it. So you can see I have two sentences. This is H2, this is H1, original Hausa. So now you have two sentences. So this is data augmentation. You create more sentences. So these are what we call data augmentation approaches, which basically, allow you to create more data, right? From sample instance. Yes, engineer.
But sir, how do we handle the grammatical error that may come across? It's possibly that we're going to get some grammatical errors. So how do we tackle that one? Yeah, how do you tackle the issues of grammatical error that may injected into when we are trying to bring in some word into?
That's a good question. Yeah. So he's asking, how do you handle grammatical error correction? You need to correct that one. If you are using human, if it is human, so human can translate that and make sure there's no error. If you are using machine translation, you need to correct errors after doing the translation yourself. So inevitably, if you are using machine, something can creep in and you can have issue with that. Yeah. Yeah, so that's some approaches to do. We have another one, noise or token level foundation, which is also another approach. For example, uh, in the source set, for example, I said, zan je kasuwa gobe na so agogo. So another approach is that zan je kasuwa gobe na so agogo. Another approach is you can swap, delete, or insert word in the source sentence. So maybe I can say, zan je kasuwa gobe na so agogo, the last sentence I deleted. So you can see you have now two different sentences. Zan je kasuwa na so agogo is one sentence. Zan je kasuwa gobe is another. So you can see there are two different sentences. Because wannan ya ce zan je in so kasuwa in zuwa, wannan kawai ce zan je kasuwa. So maybe ko kuma ka ce zan je kasuwa gobe na so kaji. So now you insert words. Can you see that you insert word? This is what we call noising or token level perturbation. So help model learn robustness to typo or variation, right? So this is something, another approach. We have another thing. So there are different kind of data augmentation. So what brings us here is that we are talking about how can you create a machine translation corpus. Parallel. We say you need parallel corpus, and if you don't have enough parallel corpus, you need to do data augmentation in a way. Yeah, so that's it. And for machine translation, for NLP data augmentation, we have different kind of libraries. NLP text attack, OpenMT, Hugging Face, and so on, that can use model for doing paraphrasing and synthetic data generation. All these approaches can be used to create more data set. Yep. This is also one of the data going machine enhanced back translation for low research. This is one of the paper from Idris. He did his PhD in machine translation. So he did what we call enhanced back translation for low research neural machine translation using subterranean, something like that, to create a back translation approach. But we can also use LLMs to generate data. For example, you can GPT or to create more example of data. But the problem is that the data may be biased, or in generated data, it may not be of high quality. If you use LLM to generate data, the data may not be of high quality. And, yeah. So you can also create this synthetic data. As I said, these are some of the papers, synthetic data for low resources. You can see that there are many work now for creating synthetic data using LLMs. And finally, we have 12 minutes. I added 12 minutes. Okay. Yeah, converting active to passive sentence and vice versa. Also, that will create, parallel something augmentation. Now, let's quickly look at this final part about, evaluating machine translation system. So for example, if I have machine translation, it's going to be difficult if you say, because a translation system might have multiple, multiple translation which are correct. So the translation might be difficult. A sentence may have multiple translation, correct translation, and also language differ in syntax and word order. Literal meaning may not reflect semantic correctness. So there are many ways to do that, but evaluation for machine test is difficult. One of the key things that people do is human evaluation. So we have human evaluation. When you do train machine learning system for machine translation, one of the way to evaluate how good it is use human evaluation. This is the most reliable approach, and human are translated based on. So what you need to do is, you evaluate the machine translation system using two, metrics: adequacy and fluency. Adequacy. So when I translate from Hausa to English, what I need to do is to get some people, pay them, and then ask them to gauge the translation based on its adequacy and fluency. That is how much meaning from the source is preserved. Like the meaning of translation, is it preserved from this English to Hausa? Is it preserved? Fluency, how natural the translation sound in target language. That is, when the translation, how natural the translation, does it sound like natural, like human being, or does it sound like a robot? So you ask people to gauge the accuracy. For example, you can give them like a scale. For example, you can say from 1 to 5, how adequacy this translation is. From 1 to 5, for example, the meaning is preserved. If it is preserved really well, excellent, you give it a 5. If it doesn't, you give it 1, meaning that it changed meaning. Fluency, how natural is it? Like human translation, like man? If you can say from 1 to 5, choose fluency. So these are the a most reliable way to evaluate human machine translation, right? But one key thing is that human evaluation is the most expensive because you need to hire people, give them money, and it's gonna be slow. It cannot be scalable. For example, you have 1 million sentences, therefore, human evaluation is really, really difficult, right? You need an automatic way, right? Where you maybe use some system to automatically evaluate the correctness of machine translation system. So, in a way, human evaluation is the most accurate. You don't have any substitute. Yeah, you don't have any substitute to evaluate the correctness of machine translation rather than the human evaluation. But it's most, expensive, slow, and you cannot scale. So you need automatic approach. For example, in other machine translation system, we use F1. We use what other method do we use in classification? Can somebody tell us? Do we all know what is evaluation metric?
Precision.
Yeah, something precision. Okay. Um, yeah, so evaluation metrics, we know these are something that we evaluate our machine learning system, such as, as we talk about precision, F1 score, and other stuff. So we need those one. But in machine translation, we have what we call lexical overlap metrics. We have what we call edit distance. We have semantic metrics. These are some of the things we use for machine translation. We don't actually use F1 or, all other metrics. These are some of the automatic machine translation evaluation system we use. Lexical overlap. So what is lexical overlap? Lexical overlap, we use a metric called blue orange. I don't know how to say this because it's French word. So in lexical overlap, as I said here, we have one lexical overlap. What this means in lexical overlap is that it try to check the overlap of the lexicon. So um, we have what we call blue. So blue core idea is measure the n-gram overlap between system translation and reference translation. Do you know what is system translation and reference translation? So what this means is that let's assume that this is original sentence in Hausa, original sentence in Hausa. And this is the original one. And then I use machine learning system to translate to English. This is English. Now, this one that already machine learning system translate is what we call system translation. System translation. System translation. But my Hausa, original Hausa that I want to translate, because I want to evaluate it, how good machine learning system is. I already translated this one by human. This translation by human is what we call reference translation. That means that you are going to reference this translation to see that is it the machine learning system translation is good. You're gonna reference with this translation that man translate, right? Now, so this is the translation done by man. This is the translation done by machine. This is called system translation by machine. This is the translation by human. This is this one. So what blue does is that maybe here something I translate this one to, is I love this car. Maybe ina so wannan motar, something like that, right? So, but this is what this human translate. I love this car. Ina son wannan motar. But this is, for example, what machine translate. Machine translates something like this. Um, uh, so nan na ce ina son wannan motar, maybe nan ya ce How can somebody tell me this one in
Ina
different way?
muradin wannan mota.
Yeah, so something like that. Ina muradin wannan mota, ina muradin wannan mota, something like that. Ina muradin wannan mota. Now, what blue does is that it compare unigram, bigram, and compete how often they occur. So this is translation by human, this is translation by machine. Ina muradin wannan mota. If we are using unigram, we can say the first one inner, that we have inner in human translation and we have inner in machine translation, which is good. So the system will output this is one good. But muna so muradi, it doesn't appear in both, right? There is no computer. So this muna. But wannan and wannan appear here. Motor and motor appears here. So if we use unigram, that is you compare only one word. That means this is a good translation because it's only one word that is missing from the human and what machine. I don't know if you understand what I'm saying. So you can see the core idea major n-gram overlap. We know what the word means overlap, right? N-gram overlap between system translation and reference translation. So between reference translation, the one that man did and the one that machine did, it compare the overlap. Do we have overlap between machine and human? So yes, of course, when the overlap is high, is this the translation is good? Can somebody tell us the answer? When the overlap is high, is the translation good? When the overlap is high, is the translation good or no?
No, sir.
It's not good when the overlap is high?
Yes, sir.
No, it's good. It's good.
Eh?
I think it's good when there is so many overlaps.
Yes, exactly. I think when there is so many Musa Adamu, is the translation good if that we have many overlap?
Yes, doctor. It is good because there are a lot of similarities between the two sentences.
Exactly. So because this is translation by human, by man, this is the translation by system, computer. And now we say, okay, let's look at the overlap between the translation by man. We have inner by machine. Son and Muradi, they are not overlap, but one there is one motor there is motor. So out of 4 words, 3 overlapped. Only one didn't overlap. That means the system is good because it overlapped. We have translation between man and system 3 instances. So the translation. So this is what we call blue. This is what blue bilingual evaluation study. If you are working on machine translation, this is one of the most widely used evaluation metrics in machine translation system. So here we use unigram, but you can use also the system can use bigram, trigram. Bigram means we combine 2 words. Inner so. So you combine this word. Do we have inner so from machine translation, human translation, and inner so in it depends on the blue style you use, whether unigram or bigram. So that's one, evaluation metric, and blue is one of the most widely used evaluation metrics in NLP for machine translation. Wherever you see blue is this, yeah. All right, so let's go on. Okay, this is the example I gave. We have edit distance. So edit distance is basically, we have another this one, which is Rob. Okay, they are basically the same, but this is what we have. Edit distance metric. So what this edit distance metric does? So edit distance measure the number of edit required to transform system output into reference. So measure the edit need to be done to transform system output into reference. So for example, now we have system output here. We have reference output here. How many edit are we going to do on this system output to give us exactly the same as human output? How many edit?
One edit.
One edit. So if we have one edit, so the more edit we have, the worse the system is, right? But the lower number of edit we have, the better the system is. Is that correct?
Yes, it's correct.
So here we can see the number of edit required to respond system output into reference range is possible edit. It can be insertion, deletion, something or what. So you can see here is just we can do deletion of something to So this is what we call tar. This is an example of that. So then semantic metric. So we have another semantic. So you can see this one. What we are doing here in blue, it is trying to find the exact reference. For example, this and this. Do we have this and this? But there's key issue with that. If you look at this one, ina muradin wannan kaɗin da ina son wannan kaɗin, do they mean the same thing? A Hausa mu, do they mean the same thing? Do they
No,
convey the same meaning?
no.
They convey the same meaning, only that it looks like there are dialectical variations.
Yawa. It means this ina son wannan kaɗin, ina muradin wannan kaɗin. A Hausa, in Hausa is they are all they convey the same meaning. Is that correct?
Yes, yes, bro.
Yes, yes.
Right.
So in that case, we can see the blue here fell. The blue fell. It doesn't give us perfect say, oh, these are the same. It just like, give us like, yeah, they are near meaning because it only fell in one instant. So can we have an approach where it can not only measure the lexicon, occurrence of lexicon, but it will just measure the meaning. If the meaning are the same, it will say this is good translation. Do you think this is a good way?
Of
Not
course,
to
it's a good one.
not to compare only the like number of lexicon
Mhm.
that appears, but compare ina son wannan motar, ina muradin wannan motar. If it compare these two sentences are correct, like they mean the same thing, then it can give it a high number of accuracy rather than to compare the number of lexicon matches overlap. So if we can do that, this approach, which we call semantic metric, from the meaning, from the word semantic mean meaning. So
Mm.
semantic metric evaluates semantic similarity using embedding or neural models. So this metric is called semantic metric. It just evaluates semantic meaning. So if you have two sentences, if you have sentences, you just you what we call bad score. So bad score is one approach that you can calculate the bad score for two sentences. If the score is high, then that two sentences are near in meaning. So for example, that one we have, ina muradin wannan motar and ina son wannan motar, the bus score will be really good. And we also have another comment, also is the something is semantic meaning that do that. So you can see here context BART score compare contextual embedding from transformer, encode semantic system, encode system translation and reference using BART, compute similarity or what aggregate the similarity score. So you can see it advantage handle synonym and paraphrase. So it can handle even sentence, for example, you can see Muradi and Inaso, they are just synonym. So if we use bad score will consider in so and Muradi, they are the same. And it can say, okay, these sentences are correct. So also Comet this did the something, is a neural evaluation. So this also are basically the same. Okay, so I think we can stop here. We can continue, with attention mechanisms tomorrow to continue understand the problem. Any question? All right. So this today we basically understand, we understand Seq2seq model. We understand contextual vector. It has some issue. It introduce what is called bottleneck. Information bottleneck, and we need a way to solve this problem. The problem of bottleneck, problem. So tomorrow we are going to look at this bottleneck issue. How do we solve it? By what we call attention mechanism. This attention mechanism is a little bit, it's a little step toward the real transformer architecture. And on top of that, today we now have seen a little bit about one of the widely used Seq2seq application, machine translation. We discussed a bit about machine translation, how we can evaluate machine translation system, how we can create data set for machine translation system. So without much further ado, I think, if there is any question, let's listen to the question. But if no question, we can meet tomorrow.
It's like Musa that will have question.
Okay.
Assalamu alaikum, doctor.
Yes.
I want to ask, after successfully developing a corpus, there is need for one to validate that model according to you. There is need for you to evaluate the corpus to ensure that it is robust and well developed.
Yes.
That is benchmarking. There is need for you to develop models to test it personally, not just leaving the corpus and say it has been deciphered following all the required procedures and technicalities. You cannot just leave the corpus like that. There is need for you to develop other models by yourself to ensure that and put that in practice before you release the model. Is that necessary? That's what I want to learn, please.
Come up over again the question.
I said after successfully developing a corpus for certain
tasks.
tasks.
Yes.
From what I've been studying, I observed that there is need for you to develop models to benchmark what you have done and compare it against existing corpora related and other things.
Yeah. So that's So that's what many people do. Like, if you want to do benchmarking, you cannot do it without data set. So the first thing is for you to create data set and then you do benchmarking. So for example, if I want to benchmark LLMs, for example, current LLM, how good they are in translating sentences from um, you know, uh, you know, uh, in translating sentence to Hausa or something like that. So you need to basically create a corpus from the beginning and then you do benchmarking. So we'll have a benchmarking lesson at the end of the day. So we'll discuss more about this on benchmarking. So let's just stay tuned about that. We're gonna have benchmarking class, something dedicated for benchmarking. Yeah, we'll discuss this more in detail.
Thank you very much.
All right. Thanks, everyone. And let's meet tomorrow and continue the discussion. See you tomorrow. Bye bye. And okay, Lukman, can we have our practical session today? Or you don't, or we start from tomorrow?
Start tomorrow, sir.
Okay, so everyone, we're gonna continue our practical session tomorrow. We're gonna do PyTorch tomorrow. Yeah, see you tomorrow. Bye bye.